Good evening, students. This is Deekam Pathak from Freebirds Experiences. I welcome you all to this wonderful series called Fun with NCERT. So today's session will be taken by Ms. Nupu. Ms. Nupu, so without any further ado, Ms. Nupu, please continue on with the session. Thank you.
Thank you, Deekam. So I am Nupu Chaudhary. I work as an assistant professor in the Department of Computer Science and Engineering, Assam Don Bosco University. So welcome to today's session. So we will be, let me first share my screen so that we can see what is the topic of discussion today. Okay, so I believe you can see the screen. Deekam, would you confirm? Okay, so the topic of discussion today is gravitation. So we have been hearing a lot about gravitation in our day-to-day lives. Also, there are a lot of practical applicabilities of gravitation. Okay, so today we will be talking about this particular force in detail, or this particular property in detail. Okay, so let us get started. So as you can see in this particular slide, there is a person who is trying to drop a ball, or who is dropping a ball as well as a feather from a certain height. Both this ball as well as this feather travels a certain amount of height and reaches the ground. Okay, so this picture is demonstrating a classical example of gravitation. Whatever, if we drop it from a particular height, that will reach the ground. Okay, it will not go anywhere else, but it will reach the ground. Similarly, in the second picture, if you see, this is picture number 1. Okay, so in the second picture, if you see, this man is trying to throw a ball, okay, at a certain angle. This ball also will travel to a distance, okay, and eventually it will go down and hit the ground. Right, so this, let us consider this as ground. So it will hit the ground. Why doesn't the ball go straight, or why doesn't the ball go up? Okay, why these two directions are ignored, or it is followed for some amount of time, and finally the final destination of the ball is to reach the ground. So we have to understand that the underlying phenomenon behind this is basically gravitational force, or the gravitational pull, which is acting on this particular ball, and as well as this ball and this feather. This force is continuously acting on the objects, okay, and by the property of this force only, these objects which are thrown from a certain height or dropped from a certain height comes down. Okay, let us move to the, so let us move to the next slide. So before going into details about the various things related to gravitation, let me tell you a small story. Okay, this gravitational pull or gravitational force was first discovered by Isaac Newton, okay, sometime around 1600s, okay. So what happened is that we have already heard about this story n number of times, that while Newton was sitting under a tree, suddenly an apple fell on his head, and that made him think that why the apple did not go up, but it simply fell down. However, this story is not true, okay, or it does not have any evidence that the apple straight away fell on Newton's head. So basically what happened was, when Newton was in his university, so there was a plague condition all over the country, okay. So he was in Cambridge University, so he had to return to his home. So while he was on a walk in his garden, he saw that an apple was falling from a tree to the ground, and that actually made Newton think that what is it which is pulling the apple towards the ground and not to anywhere else. Okay, it is not going upwards, or it is not moving in a horizontal direction, but it is simply moving towards the ground. So at that point of time, Newton started working with this concept, and he came out with the concept of gravitational force. That means a force which is continuously acting on each and every object which is present in the universe. Okay, so here in the next picture, if you see, there is the sun is in between, and the other planets are actually revolving around it. So this is also due to gravitational force or gravitational pull, that the planets are actually attracted towards each other or attracted towards the sun. Okay, so moving ahead, let us first talk about that. What is gravitation? Okay, so gravitation is basically a force with which two objects attract each other in the universe. Okay, two objects attract each other in the universe. So if we are talking about two objects, it can be anything. Maybe a pen and a box. Okay, maybe two glasses, maybe a table and myself, or the person who is standing beside beside that particular table, right? So it is just a force with which two objects would attract each other in the universe. Okay. Now the question is, why, if two objects are continuously attracting each other, then why don't these two objects stick to each other? Okay, so let me first switch on the camera, and then I can actually show you with the demonstration. Okay, can you hear me now? Okay, so just yes. So can you see me? I think you can see me as well, right? So these are the two objects that I'm talking about. Okay, these are just the example of two objects. So this box, this small cube, okay, and this pencil, both of them are getting attracted towards each other because of gravitational force between them. Okay, even I am continuously attracting this pencil. This pencil is continuously attracting me. Okay, let's consider this glass. So this glass is continuously attracting the nearby object which is near it. Okay, if I keep the pencil near it, it will be continuously attracting this pencil as well, this glass. So this is basically a force which is continuously attracting each other. Okay, now going back to my question, that if these two objects are continuously attracting each other, then why don't they just stick to each other? Why are they separated? Okay, why can we place both of them in two separate positions? It should come to our mind that both, if it happens between two objects in the universe, that means there is a force between these two objects, and if there is a force between these two objects, essentially that pull should have made them stick to each other. But this is not the scenario. The question to this answer lies is that this force, this gravitational force, is a very weak force, okay, and it entirely depends upon the mass of the objects. Okay, so this is a very, very weak force, as well as a non-contact force. We have done about different types of forces in my previous session, okay, which included, let's say, muscular force, electrostatic force, magnetic force. Okay, so there you do not have to have contact between the objects, right? In magnetic forces, you do not have to have contact between the objects. So likewise, this is also a non-contact force. Okay, so it do not need to have contact with each other, but it is continuously getting applied on each other. Okay, similarly, we are also getting attracted towards the earth. How? Now I have a ring, and if I drop it, it straight away goes to the ground. Now in this case, the ground is the table. Okay, it is slightly elevated. Now if this table would not have been there, it would have straight away gone to the ground. Okay, now our earth has this gravitational force, and it pulls the object towards it, because the earth's gravitational force is higher than any other forces which is applied on this particular object. Okay, so that is the answer to the question, that they do not stick to each other, because within each other the force is very, very weak, and they are getting attracted to the ground because the gravitational force, it depends upon the mass of the objects. Okay, this has a lower mass than what earth has, so that is why this pencil is getting attracted towards the ground. All right, so that is why it does not get stuck to each other. Okay, so moving ahead with the rest of the presentation, let me simply share my screen again. So what we saw is that we already saw that it is the weakest fundamental force, and it will definitely act due to the masses of the body, which is taken into consideration. So mass plays a very, very important role. So the bigger the mass is, the bigger is the force. Like I already gave you the example, the earth has a higher mass than what the nearby object has. That is why the pull towards the earth is greater, and that is why the objects will fall down. Okay, so if we have this concept, then there must be a question which should arise in each of us. Okay, if any two objects will attract each other, do we also attract the earth? Okay, so this is by Newton's third law of motion. Every action has an opposite and equal reaction. So if I consider a human being, okay, a man, and the earth, so if the earth is continuously pulling the man towards it, is the man also pulling the earth towards it? The answer is yes. It is also pulling the earth towards the man, but as already mentioned, this has a higher mass, okay, than what a small man or a small human being has. I mean, a particular individual would have, and that is why the pull towards the earth is greater, and hence the man will be attracted, or he is stuck to the ground if he strikes the ground whenever he falls from a particular height or he jumps. Okay, so that is the answer to this question, that if two objects would attract each other, we also attract the earth, because we also have certain amount of force between us and the earth. Okay, but the earth will have bigger mass, or it has bigger mass, and that is why the person is pulled towards the earth, and the significance of the earth's pull is very, very minimum. Now, moving ahead with the universal law of gravitation. So this is something which each and every one of us should remember. Okay, so here every object in the universe attracts every other object with these 3 points. Okay, so these 3 points, the first point is a force which is proportional to the product of the masses. Suppose I have two objects, M1 and M2. So here, what is the first point saying? The first point is saying the force which is proportional to the product of the masses. So the first point is F is proportional to the product of the masses. Okay, and the second one is that the force which is inversely proportional to the square of the distance between them. So this has a certain distance, right? So force is inversely proportional to the square of the distance between them. And the third one is that the force is along the line which joins the two objects. So the force is not somewhere from this point or this point. Okay, it will be along this line which will join the center of the two masses. Okay, so now, or the center of the two objects. Now let us see this in a diagrammatic way so that it is much more easier for us to relate. So if you can see this picture, Earth has mass m, as I mentioned already. Okay, this is the first object which is mass m, which has mass m, and the second one is another object which has small m as the mass. Okay, so what would be the force? The first point, the first point, it says that it is directly proportional to the product of the masses. So this is the product of this is the mass of Earth and this is the mass of the object, and it will be inversely proportional to the distance between the objects. So this is the distance which is represented as r. Okay, so it is inversely proportional to the square of the distance between them. So the final formula or the final universal law of gravitation states that this is the final formula. However, in order to remove this proportionality constant, you might have already done in your previous classes that in order to remove the proportionality constant, proportionality, we have to introduce a constant. So in this case, G is the universal gravitational constant, okay, which is introduced, and G has a value of 6.67 into 10 to the power minus 11 Newton meter square per kg square. All right, so hence the final formula is this, which is already mentioned here. Okay, now I believe this much is clear because this has nothing much to understand, but we have to remember these things, that it is directly proportional to the product of the masses, inversely proportional to the square of the distance between them, and in order to remove the proportionality constant, proportionality here, we will be introducing the universal gravitational constant, which has a certain value, which is 6.67 into 10 to the power minus 11. So this is a constant and it will not change. For Earth also, the G value remains same. If you go to Pluto as well, the G value will remain same. Even if you go to other, like the nearby Andromeda, if we go there also, if we take out any planet from there, maybe there also, not maybe, actually the G value there as well remains the same, right? So what is the significance of this gravitational force? These are just four significance which I have mentioned. However, there are a lot more to be explored. So all of these are mentioned in your textbooks. So if you go through them, it will be easier for you to remember as well as learn as well. Okay. So what is the significance of this gravitational force? Is that, or gravitation is that, first of all, it binds us to the Earth. Only because the gravitational pull or the gravitation is there, this force exists, we do not bounce up and down like what happens in case of the moon or in some other planets. Okay, we can simply walk on the ground. It binds us to the Earth. We do not simply fall off. Okay, the second one is motion of the moon around the Earth. So there is the Earth and we have the moon revolving around it, right? So this moon is actually bound to the Earth because of this gravitational pull from the Earth. Okay. Then motion of the planets around the sun. This is another significance, which is because of gravitation. Planets can revolve around the sun because of the gravitational force. Then the fourth point is the tides due to moon or sun. So all of us might have heard about the high tides or low tides in the sea, right? So what happens is that during this, the gravitational pull, okay, gravitational pull or gravitation is higher, or the distance between the sun and the earth, or moon and the earth, becomes less. So gravitation increases, hence the water goes up the sea level or down the sea level. Okay, so these are some of the significance. Now, moving ahead, before we talk about acceleration due to gravity, okay, we will have to understand that if there are two objects, suppose if there are two objects, I'll show this with the video so that it becomes easier to remember. So now, suppose I have considered these two objects, okay, and I'll just consider maybe these two, okay. So these two objects. So when I'm considering these two objects, we have to understand that the bigger the distance between them, that means the second point, that is, it is inversely proportional to the square of the distance between them, okay, between the objects. Now, what do I mean by that? I mean by that statement that if these objects are closer to each other, that means the distance between them is less, then the force will be more, okay. If the distance between them is more, the force will be less, okay. The first point, it states that it will be directly proportional to the product of the masses. So I'll combine this mass along with this mass, okay. I'll take a product. The force, that means the higher the mass of the object is, the higher will be the gravitational pull, okay, or the gravitational force. And the more the distance, the lesser will be the force. So these 2 points we have to remember, okay. The higher the mass, the higher is the force, and the lower the mass, the lower is the distance, the higher will be the force. Okay, so if I bring it very near to each other, the force which I will experience is much higher between both these objects. If we have a parameter or if we have something to measure with, then the force would be much higher. All right. So now what we will talk about is the tides. As I already mentioned about the tides. So what happens is, maybe this is the sun, okay, or maybe this is the earth, and the moon is somewhere going on a revolution around the earth, right? So what happens is that during certain times, the moon will come very close to the earth, okay. At that point of time, there is a increase in gravitational force which will increase the tides or increase the water level from the sea, which will cause the tides. All right, which will cause high tide, and if it goes farther away from the sun, it will cause lower tides or low tides in the seas. So this is the phenomenon behind it, because it is entirely ruled by the laws of gravitation, okay, or the gravitational law. So if we consider the next topic of discussion for today, that is acceleration due to gravity. Now, first of all, when we talk about acceleration due to gravity, we have to understand that there is a concept or a phenomenon which is known as free fall. Okay, so free fall is anything if we drop from a particular height, that object will simply hit the ground without the effect of any other force except for gravity. So if an object is falling on the ground or getting attracted towards the earth purely based on gravity, we call it as a free fall. That means we are not applying any force, additional force into it. We will simply drop an object. So if we consider an object, consider free fall, this is what a free fall would look like. Okay, if I drop it from a position, I'll simply drop it. Okay, so this is what a free fall is. Now, if I apply force into it, then that is not free fall. Okay, so if I apply some force into it, that is absolutely not free fall. But if we apply some, if we simply drop that particular object from a position, then this is free fall. Okay, so this free fall, it happens entirely due to the concept of gravity, or entirely due to only the effect of gravity. Okay, now if you look into this man here in this slide, he's falling from the sky, I mean falling from somewhere. So there is no other force which is applied on him. He will simply reach the ground only with under the effect of gravity, right? So acceleration due to gravity is a very, very interesting concept. Now, if you look into this picture, okay, if you look into this picture, this particular man is dropping a ball from a particular height. Until and unless it reaches this ground level, it will reach different position. Let's say this, and this. So at each of these positions, the velocity is actually changing. Okay, here you can see 19.6. In the next position, you will see 29.4. In the next position, 39.2. And before it reaches the ground, it reaches a velocity of 49.0. If we look into the change, the trend of it, the velocity is continuously changing, and it is increasing as it reaches the ground. And when it reaches the ground, of course, the velocity becomes 0. But before it reaches the ground, it will attain the maximum value. Okay, so it is maximum just before when it reaches the ground. Now, the interesting part about this is that if a ball is dropped, okay, and the velocity is changing at different positions, that means the acceleration will also change. Okay, so the acceleration will also change. Now, this acceleration will be because of gravity. Okay, this acceleration will be because of gravity, and we call this as acceleration due to gravity. Now, if we look at the universal law of gravitation, you will see that it is represented using F is equal to gmm by r square, where m is the mass of one object, small m is the mass of another object, g is the universal gravitational constant, and r is the distance between these two objects. Now, if I'm considering the Earth, okay, if I'm considering this Earth, and I consider there is an object A here and another object B here, okay, so now the Earth is pulling this object as well, and the Earth is pulling this object as well, right? This we have already done, because we understand that the Earth is pulling everything towards it because it has a higher mass. Now, if we represent the gravitational force for A, it will be something like F is equal to G M. M we will keep it as the mass of the Earth. Okay, Ma by, let's say the radius of the Earth is R, so R square. Okay, again for the second one, which is the object B, this is for the object A. Okay, for the object B, what we have is F is equal to Gm and then M of B by R square. Okay, so what is common here in both of them? So this is for B. So in both of these equations, what is common? Gm by R square is common. Okay, Gm by R square is common. So this Gm by R square is actually written as the acceleration due to gravity, which is G. Okay, acceleration due to gravity, which is G. So the force can be represented as mg, where G is the acceleration due to gravity. Okay, so I think this is clear, and we have to remember that this G, the capital G, is basically constant. It does not change if we go to other planets. Okay, however, this small g will change. Okay, this is not constant. This is a changing factor. All right. Okay. So the next one that we will be discussing is center of gravity. So when we are talking about center of gravity, basically it is a point through which the entire weight of the body acts. Okay. So all of us has certain amount of weight, but our weight is basically acting on a certain point, a point at which all of our weight is acting on it, so that if we are standing above the ground, that body is balanced, or we are balanced and we do not fall down. Like you see in this picture, these two persons are simply sitting on the edge of this particular, let's say a plank, and it is balanced in just one point. If you see this, so this is the center of gravity point, and this is basically acting downwards. Okay, this particular center of gravity is acting downwards, and it is actually balancing out the force of gravity which the earth exerts, as well as the force which our body is exerting on the earth, and it will show give us a state of equilibrium. That means we will be able to balance ourselves. So this I would like to demonstrate with certain activities. So let me first switch on the camera. Okay, so I think most of us have played with this particular bird in our houses, right? This was a toy which we found, which we used to play in our early childhood days. It is just a bird, okay? A plastic bird, okay, with two weights, which is associated with, which is embedded in this particular wings, okay? Now, if I hold this bird from this point, all right, from this point, with my just one of my finger, it will simply fall down. Again, if I try to balance this bird with maybe with its tail, this also cannot be balanced. Okay, let me remove my finger. I'll just use this, okay, glass. Now, if I'm trying to put this bird on the glass, it will fall down. Let me place the wing. This will also fall down. Okay, so then how do I balance this bird? Okay, can I balance this bird at all? Can I make it stay floating in the air? Yes, I can, with the center of gravity concept. Okay, so what I'll do is that I'll take this bird. Okay, I'll take this bird and I will simply draw a line which will just be going, which will just be intersecting the center of this bird. That means through the center of the entire body, there is a line which will, let's say a virtual line, the amount of mass which is distributed on this side and the amount of mass which is distributed on this side, these are almost equal. Okay, if it is equal, it is very good, but if it is not equal, then also it should be approximately equal. Okay, so what I'll do is, now I'll find out a point somewhere within this particular virtual vertical line that I have drawn, okay, on this bird, and I will try to balance this on that particular line, okay, or with the help of that particular line. So since I have drawn this line somewhere like this, okay, somewhere like this, now I'll choose a point within this line through which I can balance this bird. Okay, so I have chosen this point. Okay, so I have chosen this point, and when I'm trying to place this bird on this glass, so this bird will now be floating. Okay, so this bird will now be floating on the air with the help of the glass and just one single point of contact. Okay, so this is just one single point of contact. This is just one single point of contact, and I can make it floating in the air with the help of this one single point. We do not have to hold on any other part of it. Okay, likewise, we will also talk about the center of gravity after we do another experiment. Okay, So this is how things work. You can balance, okay? You can maintain a state of equilibrium, or you can balance out everything using your center of gravity phenomena. All right. So let us take another thing. Oh, sorry. All of us have this money note, okay? Let me consider this note. All right. And I have another currency, which is this coin. Okay. So I will be placing this coin on this note, okay? So this, generally, if I'm trying to place this coin on this note, it will not stay. It will generally slip down, okay? If I'm trying to balance this coin on this note, it will slip down or it will fall down. Now, is there any way that I can balance this coin on this note? Right? So what I do is I'll simply bend this note little bit, place this coin over the folded point, okay? And I'll slowly try to open it. Now, when I'm trying to do this, it might take a few attempts when you do this, okay? So when I'm trying to do this, I'm trying to shift the center of gravity, or I'm trying to just identify the center of gravity point so that this coin remains balanced. So can you see, I have just opened the note and the coin is still there, which is on the edge of the note. Okay.
Miss Nupur, sorry for interrupting. Actually, what happened that we're experiencing a power cut in my area actually. So my actually it's been more than 1 hour. So my laptop will turn off like any time. so if it's okay, we'll be restarting like Mr. Ripjoti Data, like someone else from our team will be handling the session, like the technical part of the session. So he will be in contact with you, and we can restart the session like in between half an hour, if that's okay.
Okay, no problem, because I'm almost over. I mean, just a few more things to display. Otherwise, it is fine.
Okay, so how many minutes like on an average? But actually my laptop.
Another 10-15 minutes.
Oh, actually,
10 minutes is sufficient.
Oh, I think I don't think so. The laptop will be able to take it. It has like probably 5 minutes of power left actually.
Okay. I'll try to wind up within 5 minutes, then, so that it becomes easier for you.
No, it's fine. So if you want to, like, what we can do is that he can contact you, like the other guy from our team, and then you can like continue on from this point off, like from this point in time, you can carry on the session.
Oh, okay, no problem.
Yeah.
No problem.
Yeah. Sure. So
can I continue?
Yeah. Please do. Yeah, I just wanted to let you know. Yeah, in case
no problem.
In case I'm like disconnected, it means that my power is turned off completely.
Okay, sure.
And once again, apologies to the children watching at home as well. It's unfortunate event. All right. Okay. Please continue.
No problem. Okay. So you can see the coin is still there, right? Now it fell down. Okay. So like this, you can try to balance these things at home. Okay. These are entirely safe experiments you can do. So now the coin, if you see, the coin stays here because we have identified the center of gravity, the center through which all the weight towards the earth will act. Okay, and hence we can maintain a balance between the earth's gravitational pull or gravitational force as well as the force which is exerted by this body on earth. Okay, and when this force is actually balancing out, that means the force which I'm applying from the top and the force which is getting applied from the bottom, it is balanced, then only the thing will get, then only it will be balanced. It will not fall off. Okay. Likewise, there is another activity which we can do using the balancing act, or you can say the center of gravity. So what I have is, I have a spoon and a fork. Okay. I have a spoon.
Ms. Nupur, sorry for interrupting you again. Actually, fortunately, the power has come back on right now, just now. So we can continue on like comfortably. Thank you so much. And once again, my apologies for the inconvenience.
No problem.
Sure.
Thanks. Okay. So now, if you see that I have a fork and a spoon, okay, this is something which is readily available in our homes. So I have a fork and a spoon. Now, what I'll do is I'll simply attach this with one another, just like, just like this, okay? Let's say, I'm trying to do this, yes. Just like this, you just pull the edges of the fork, okay, the boundary of the fork, and you just push the spoon inside. You can use 2 forks also, it is up to you, okay? Then take a toothpick and just insert it in the joint of this particular setup. This is getting loose. It also might take a few attempts because sometimes it does not work. Okay, so now what I have done is I have attached a toothpick which is to my already existing setup. Okay, to my already existing setup. And now what I'll do is I'll try to balance this in this particular glass. Okay. So if I'm being able to make this floating in the air, that means my experiment is successful in. I don't know whether it is very much visible or not. Okay, can you see this? So this is basically not falling off. The spoon and the fork, it is not falling off from the glass. I can actually rotate it from different angles. Okay, so what is happening? The center of gravity is identified as this particular point of the glass. I'll just bring it closer to the camera so you can see. So if you see this, if you can see this, so the spoon and the fork, they are floating on the air, floating in the air. So it will not fall off because the center of gravity is not wrongly identified, is correctly identified. Okay, so if I'm putting this simply here, it has a chance to, like, see, it will not float here. Okay, I won't be able to put it until and unless I put it across this glass. But what I did was I did not put it across this glass. I simply kept it on the edge with the help of this toothpick. Okay, and it rotated freely about that particular point. So this is where your center of gravity comes into picture. Okay, now the main concept is of center of gravity is we are actually trying to balance the moments. Okay, so if we are talking about, let's say, so if we are talking about a particular bird, again, so I have a bird. Okay, so this is how my bird look like. Okay, I have this bird with me. All right, so now what I'm trying to do is I'm trying to create a virtual plane. Okay, a line which separates both of these two. Okay, so this is the right side and this is the left side. So now what I'm trying to do is the right side will exert some moment and the left side will have certain moment. Now what I'm trying to do is I'm trying to cancel out both of this. That means the weight which is on the right side is approximately same as the weight which is there on the left side. We have to understand that weight is nothing but actually the force due to gravity. Okay, the formula also says that weight is equal to mg. Okay, W is equal to mg, and g is nothing but acceleration due to gravity. Right? So you have to understand that we are trying to cancel out the weights from, not weight, actually the moment from the right side as well as the left side of this particular axis which we have drawn. Okay, and we also have to understand that whatever is points lies in this particular axis, okay, all of these points will have equal equal establishment of center of gravity, because through every point or all the atoms which are distributed